We love to talk about quantum mechanics on our show and all of the strange things that it implies about how our universe works on its smallest scales. But despite how many words we can use to try to explain quantum mechanics and the fact that we can make multiple, hour-long episodes about it, a lot of it comes down to a single, pretty short equation called the Schrödinger equation. If you were to Google this equation, it might look kind of complicated. It's got some weird symbols in it. It has a derivative, it has the imaginary unit I, but it's this single equation that is the source of so much of this quantum weirdness that we talk about, things like superposition, the uncertainty principle, and everything like that. So how is it that physicists at any point were able to come up with the Schrödinger equation? How were they able to intuit that this might explain reality at any level? Well, today we're going to try to answer that question. Today's episode will be a deep dive into the Schrödinger equation. We'll tell you one way that you can think about why this might make sense for explaining nature and what makes it so unique as an equation in physics and why it's the source of so much quantum weirdness. So if you want to peek into the true mathematical heart of quantum mechanics, stick around. You're listening to Why This Universe, a podcast where we break down the biggest ideas in physics. I'm Shalma Wegsman.
And I'm Dan Hooper. For the last couple of months, I've been teaching a course on quantum mechanics for undergraduate physics students at the University of Wisconsin. And, it's been great. I love this stuff. Since I encountered it decades ago for the first time, I thought quantum mechanics is like the single most interesting thing that I think human beings have ever come up with. And I don't just mean in physics or in science. I mean anything, any piece of art, better than anything Shakespeare ever wrote down. This is just mind-blowing stuff. Really, though, almost all of it anyway, boils down to how we use a single equation that's kind of at the heart of quantum mechanics. And this, of course, is the famous Schrödinger equation. Before getting started, I want to acknowledge that Erwin Schrödinger, who came up with the equation we're going to be talking about today, has been credibly accused of many instances of sexual misconduct involving a large number of teenage girls. I don't want anyone to think that by talking about Schrödinger and his physics here today that we condone any of this behavior in any way whatsoever. He was plain and simple a sexual abuser, and he was also a great physicist. Both of these things can be true at the same time.
So like the theories of physics that came before it, the major goal of quantum mechanics and the Schrödinger equation in particular is to describe how things change. For example, if you have some particles and they have some amount of energy, maybe this is potential energy of particles at the top of a mountain, or there's kinetic energy, the particles moving with a certain speed. You want to know what these things will do as the clock ticks forward. So in classical mechanics, we have Newton's second law, so F equals ma. And if you've taken physics in school, you'll be very familiar with this equation. This is force equals mass times acceleration. From F equals ma, this very short equation, you can figure out where all these particles are going to be in the next few seconds, in the next few minutes, hours, days, how they're all going to change in time forever. So this is what the Schrödinger equation does too. It's basically the analogous equation to F equals ma, but describing quantum particles. So the crucial difference here is that a quantum particle is not a classical particle. So instead of having a distinct location in space and velocity, quantum particles are described by the wave function. So this wave-like state that spreads throughout many locations at once. So the Schrödinger equation, in short, describes how the wave function changes in time.
All right, so let's put this whole equation and their discussion around it in some historical context. So he came up with this equation in 1925. At this time, quantum mechanics was really just in an infancy sort of state. There were some of the ideas that were kind of behind quantum mechanics that were starting to percolate among a relatively small number of physicists. But I would say that nothing particularly concrete had come together just yet.
So one of these early pre-quantum ideas came from Albert Einstein in 1905. He had done research on the photoelectric effect, where shining light on a material causes it to emit electrons. And he realized that in order to make sense of the experiments he was seeing, you would have to think of light as coming in distinct little chunks called quanta, what we now refer to as photons, or the particles of light. So this introduced this idea that light, which was well understood as a wave, was also a particle. And these particles of light have an amount of energy that is inversely proportional to their wavelength. In other words, the longer their wavelength is, the less energy they have. The shorter the wavelength is, the more energy they have.
Then, about 10 years later, Niels Bohr developed a model for the hydrogen atom called the Bohr model. Basically, he said that the electron going around a hydrogen atom can only have discrete amounts of angular momentum or energy. They can only have certain amounts, not just any amount, but integer multiples of a certain quantity, okay? And if you posited this, which as best I can tell had no particularly good rational reason behind it, but if you just posit this, then you can suddenly explain a bunch of the stuff we observe about hydrogen and other elements, namely the kinds of wavelengths of light that they emit and absorb, these spectral lines that had been observed that otherwise had no explanation whatsoever. Then in 1924, a PhD student in physics named Louis de Broglie proposed that all kinds of particles, like electrons, photons, everything, behave like waves, and they have wavelengths that are inversely proportional to their momenta. This was kind of motivated by Einstein's theory of light quanta. And also, he showed that if you believe what de Broglie was saying about everything being a wave, then you could explain the reasons for why the Bohr model of hydrogen worked.
In other words, the strange feature where electrons in atoms can only have specific energies could be explained if you saw these electrons as waves, which can only really fit with certain wavelengths around the atom's nucleus. Very similar to how a pipe organ of a certain length can only play specific frequencies or tones, because those are the only tones that fit as a standing wave in the pipe of a certain length. So in that same way, the different orbitals around an atomic nucleus can only fit certain wavelengths, and that corresponds to certain energies that the electrons are able to have.
There seemed to be this emerging picture that the stuff we find in our universe, photons, electrons, whatever, are made up of things that behave in some sense like particles, but also very much like waves.
And it turns out that a lot of what makes the Schrödinger equation and quantum mechanics in general so weird is exactly that we're describing particles as waves. Once the fundamental unit is not a single point thing in space, but rather a wave, you get a very different picture of physics. So let's dig into why it's so different.
So let's take a second and try to focus in on the most important thing that physicists mean when they say something is behaving like a wave. If I just take things that are purely particles, marbles, and I take some marbles and I add some more marbles, I just get more marbles. Marbles just add together. They always add together. 3 marbles and 4 marbles or 7 marbles, whatever. But if I take 2 waves and I put them together, maybe their peaks and troughs line up with each other and I get a bigger wave. We call that constructive interference. But maybe the peaks and troughs are misaligned. So the peak of one wave is at the same place as the trough of another, and then they'll cancel out. So if instead of marbles, I add 2 waves together, I can say wave 1 plus wave 2 equals no wave. And that's called destructive interference. So this property of waves that they're able to interfere with each other, both constructively and destructively, is really the central feature of a wave that we're talking about when we're talking about particle waves and stuff like that.
So working within this historical context where we were understanding particles as waves and light as a particle, how did Erwin Schrödinger put that all together and develop the Schrödinger equation? Of course, we can never know for sure, we can never get into his head, but we could try to take some guesses.
So I sat down, tried to get an inkling for how somebody might do this. And, the first thing a physicist notices when they look at this equation is it kind of takes a form where like there's a number that looks like the total amount of energy, and that equals something that's related to the total kinetic energy or the energy in the motion of the stuff, and then the potential energy. That makes sense. That's kind of what we would expect. And you can write the kinetic energy part in terms of the momentum of the object. So we have something that's a total energy related to something having to do with the momentum, plus something related to the potential energy.
And so far, all of that stuff is the same as any classical
so far
sort of marble scenario, right? We're still just talking about like the total energy of the system, and it's related to both the motion of the system, its momentum, and also its potential energy.
Yeah, so far this is all like very familiar to a student of classical physics. It's nothing too weird yet, but that's all about to change. We need to make progress in writing down a wave equation, something that describes the evolution of waves in this with this energy relationship. We need ways to represent the momentum and energy of these particle waves in terms of things that the equation is describing, which is what we call the wave function. We'll come back to the wave function a little bit later in this episode, but for now, just think of it as the thing that describes the shape of the wave that's evolving. So I can write down an equation. A simple equation describes how a plane wave, the kind of simplest kind of wave, just moves forward through space. It describes where the peaks and troughs are, and depending on the time and position. Okay, that's all good. And now we can put into that some conditions. We can make sure that it has the same amount of energy that Einstein said a light quanta wave should have. And we can make sure that de Broglie's condition is satisfied too, that the energy of the wave is equal to the Planck's constant over the wavelength. And we can kind of force that into the wave equation. And now we have a very specific kind of wave equation.
So we start with just the idea that what we're describing is a wave. When we describe a quantum particle, you can even visualize like a wave in a pond or something if you drop a rock. So that's the starting assumption, is that a quantum particle is a wave. And then we already know how to describe the wave in the pond. So we just take the same exact equation, but this time, instead of the energy of the wave relating to, how hard you throw the rock in the water or the size of the rock, it relates to the features of light, how fast light moves, and how that relates to its wavelength and other things, its color.
And now, I'm staring at these things. I'm trying to figure out what to do next. So I ask, how does this wave change with time? And how does it change with space? Okay, so just this mathematical operation called a derivative. And when I do this, I find that the derivative of this wave is directly related to its momentum. The derivative of it with respect to position is directly related to its momentum. And the derivative of this equation with respect to time is directly related to its energy. So now I'm starting to see stuff I can put back into this energy equation. And lo and behold, what comes out is the Schrödinger equation. So let's take a step back. I promised before that we'd kind of say some more words about what this wave function thing is. I just said it's like the shape of the wave, but like, what does that mean when we're talking about an electron or something? In classical physics, when we talk about objects, particles, whatever, they're described by their position and by their velocity. Okay, that's all there is to know about a point particle in classical physics. In quantum mechanics, we don't talk about point particles in the same way. We talk about wave functions. Those are like the fundamental objects that exist in quantum mechanics. And these wave functions describe the probability that you'll find the thing you're looking for, an electron or a photon or whatever, at a different place at a different time. So the wave function's amplitude, or the size of the wave function at a different place at a different point in time, tells you the odds that if you do an experiment that you'll find it to be there. You can also use the wave function to find the probability that the particle will be found to have a particular velocity or energy or momentum or whatever quantity you're talking about. All that is contained in the wave function. But it's fundamentally probabilistic. It doesn't tell you exactly where you'll find it every time. It tells you the probability that you'll find it in different places at different times.
So typically with waves, like our water wave, there's a medium that the wave is traveling through. The wave's kind of like energy that's rippling through the water, or, maybe it's through the wind or whatever it is. But in this case, we're talking about fundamental quantum particles, like the fundamental particles of the universe as waves. What is it that they're waves in? What is their medium?
There's no medium. It's not waving through anything. The wave function of the electron is, in fact, the only thing there. It's not moving through something. The electron is the wave.
And that's like a strange thing to wrap your head around. So in some sense,
oh yeah,
to make sense of, okay, if the wave is not moving through any medium, what's the meaning of it having a certain peak or a certain trough for the height of the wave, right? Like, what's the significance of that? And you're saying that's the probability of finding the particle there.
Right. The peaks and the troughs are the parts of the wave function, are the places where you're most likely to find the electron or whatever you're talking about. And the places where you're not near a peak or a trough are the places where you're least likely to find the electron if you do the experiment.
Yeah, so just, I guess, to be extra clear, the wave function is not actually the probability, but if you square the wave function, so if you take this wave that's up and down, up and down, up and down, and then square it so that it's all kind of up, right? So all the negative numbers square to positive numbers, so nothing's below zero anymore. Things can just be at zero or greater. That's the probability.
That's right.
So actually, like, the physical significance of the wave function before you square it is kind of... Is it right to say that it's a mystery, or it's not well understood?
We know what to do with it. So a philosopher would say this is a useful theory. This is a theory that we know how to make any prediction we want to make with it. Like, so we know how to use the theory and relate it to observables, but we might debate until we're blue in the face about the ontology of the theory, or what the wave function really is, and like what it really means. And we're not going to talk about it today, but there are all sorts of interpretations of quantum mechanics and what it all means. We've talked about that in earlier episodes. But I think physicists could talk about that a long time without reaching consensus, because at some level, there's no answer to the question, at least not an answer that we can get used from the scientific method, about what the wave function really is. We just know how to use these ideas to make concrete predictions that are accurate about what electron will do in a laboratory or something like that.
I wonder how similar it is to just saying, like, what is energy really, or something, or what is mass really?
Sure. We just know how to use it to make predictions, right?
That's funny. It kind of sounds like a politician evading answering real questions.
But the difference is here we're being completely truthful. We could just tell you that we know the answer and it's this. And some people, maybe lazier people than us, would do that. But we're not sure what any of these things are.
So maybe this is a good time to bring up imaginary numbers, because when we say that the wave function has an amplitude that we can't make sense of it unless we square it and associate it with probability, mathematically, this is because the wave function goes up and down, not in real numbers, but in the number line of imaginary numbers. So its amplitude, or its height, is equal to the imaginary unit I, which is the square root of -1, times some number. And imaginary numbers, while they're super common in physics and math, don't really have anything physical that you can map onto them.
I think to physicists, this is a lot less worrisome than it is to most people. And the good news is, despite all these imaginary numbers in the Schrödinger equation and in the wave functions themselves, if you use those equations to calculate an observable quantity, like the position of something or the energy of something, the momentum or something, whatever, you always get a real number, something with no imaginary piece. You can think of an imaginary number, or a complex number, which is a combination of real and imaginary numbers, just as a way of keeping track of two numbers at once, the real part and the imaginary part. So it just kind of makes this equation more powerful. You find it in a lot of places in physics. This is just one example of that.
Mm-hmm. So in other words, instead of having one number at every point, you have two numbers. There's like the secret number that you can't directly, we'll say you wouldn't directly observe. It kind of captures this like hidden complexity in quantum mechanics, where there's this, I'm going to say dimension. I don't mean a spatial dimension, but I mean a dimension of numbers that you can't directly access, but which are like secretly guiding the behavior of quantum particles.
And we call this the complex phase. of the wave function, right? That's the secret information that you don't end up really measuring, but it has an important role in kind of guiding how the wave function evolves.
Yeah, and then when you do measure it, you kind of destroy that complex phase, right?
That's right. Yeah.
So it's like this information you can't seem to access no matter how hard you try. You can only destroy it.
But it does a lot of stuff behind the scenes. We can't build quantum mechanics without it. So yeah. Wow, this is starting to sound mystical, but I promise you it's not, or at least it's well grounded in an empirical science, I promise.
There does seem to be like this extra information or something, and people are using it now to like try to do quantum computing, but there seems to be this extra information in the theory of quantum mechanics that isn't there when you're just talking about classical marbles and things, you know?
So it turns out that there are other kinds of quantum wave equations that you could have written down, right? You could have taken other kind of well-motivated starting points and derived other kind of quantum mechanical wave equations. One might wonder, like, why did nature pick this one to be manifest in its laws? And it turns out the Schrödinger equation has some rather special features that might help to shed some light on this equation. First of all, it is what we would call an equation that is first order in time. This means it has derivatives with respect to time, but no second derivatives. This isn't true of necessarily all wave equations. The standard classical wave equation, the one you might use for ripples in a pond or something, is second order in time. So this is different. What this means, if I had a classical particle out there and I told you where it is, and from that information alone, I asked you, where is it going to be tomorrow? You wouldn't be able to tell me. I would have to tell you where it is and how fast it's moving. From that, you can work out where it'll be tomorrow. But in the Schrödinger equation, you don't need that. All you need to know is the shape of the wave now. And from the shape of the wave now, you can figure out the shape of the wave later. Physicists call this unitary evolution, and it's kind of important to make this whole thing like hold together logically. Because if it weren't the case, if the Schrödinger equation had been second order in time instead of first order, then the total probability of all possible outcomes all added together would change with time. When we derived the Schrödinger equation, we wrote down this like classical notion of energy. Energy equals kinetic energy plus potential energy. If you had instead used Einstein's relativistic notion of energy, energy has a kinetic piece that looks like momentum times the speed of light, and a mass piece equals mc squared. You add the squares of those together and take the square root to get the total energy. If you did the same procedure I did to get the Schrödinger equation, but starting with that notion of energy, then you get something different, the Klein-Gordon equation. And this thing, the Klein-Gordon equation, turns out to be second order in time. So it has this weird feature that doesn't seem to conserve probability. You might think that means the Klein-Gordon equation is wrong or nonsense or something, but it's not. It's completely useful. It turns out it describes certain mesons and in the Higgs boson and things like this. And it doesn't have to conserve probability because it allows for the possibility of new particles coming into and out of existence. So what's the probability of me finding the electron somewhere? Well, it's 100%. And then in the future, the probability of finding the electron is 100%. But now let's say I've got like a field of Higgs bosons, and how many Higgs bosons I have, like that can change. You can make new Higgs bosons. You can destroy existing Higgs bosons. So the Klein-Gordon equation, by being second order in time, means that you can create and destroy particles. And the Schrödinger equation doesn't allow for that. The Schrödinger equation is only talking about particles that are low in velocity and don't have enough energy to be created or destroyed. So it's kind of it preserves this kind of sense of probability, but nature doesn't always do that, but the Schrödinger equation always does.
In the case of the Klein-Gordon with our field of Higgs bosons, if you had the probability go above 100%, then you'd say, actually, there's more than one Higgs boson here. And if you had the probability go under 100%, you'd be like, there's a chance that there's no Higgs boson in that space.
Exactly right.
And so that lets you change probabilities. And you're saying that the core difference, you framed it as like we're starting with Einstein's notion of energy. But another way to say that is also it's relativistic.
Exactly. Well, Einstein showed that you can take energy and convert that into mass. You can create particles out of energy, right? And you can take mass and make them, to destroy them and turn them into other kinds of energy. In the classical notion of energy, there's nothing like that. And since we built Schrödinger's equation on the classical notion of energy, you can't destroy or create particles, and that means probability is conserved. It's unitary evolution. But if you had done that with Einstein's relativistic notion of energy instead, then you can create and destroy particles, and probability isn't conserved.
Schrödinger's equation describes a quantum mechanics that is not relativistic. It's just
Right.
the quantum mechanics of things kind of moving slowly. But we actually do have a relativistic theory of quantum mechanics too. It just changes. You get things like the Klein-Gordon equation, and that's quantum field theory.
Indeed. All right, so that's one of the central features of the Schrödinger equation. It's first order in time. We've just been through that. But there's another one I want to talk about, and that is the fact that the Schrödinger equation is a linear equation. This means that if you have two different wave functions that are both valid solutions to the Schrödinger equation, then you can add those two wave functions together in any combination you want, and the result you get from that addition will also be an acceptable solution to the Schrödinger equation.
And this is exactly why the principle of superposition exists in quantum mechanics. You could have a wave function that describes a particle being in one location and one that describes it being somewhere else, add them together, and get a new, totally valid solution where the particle is in both places at once. So it could be two places at once, two locations. It could be a particle has two energies at once, two different spin directions, what have you.
So when we say that a particle can be in multiple places at one time or something, fundamentally that is true because it's a linear equation we're working with. And you can just kind of add different quantum states to each other to kind of get this notion that you can be in, the particle can be spinning clockwise and counterclockwise, or the particle can be in this energy state and also this energy state all at once in these quantum superposition states. That is because this equation is linear. As a side note, we'll have an episode soon with our friend and colleague David E. Kaplan, where he'll talk about quantum mechanics where we break the linearity of the Schrödinger equation, and some really weird stuff happens in that case. All right, so if we put all of what we said here today together, the Schrödinger equation isn't strictly the only logical possibility for an equation that could describe the quantum wave-like particles that are in our universe, but it is the simplest possible equation that these four different things are true for. So it's unitary, so it conserves probability. It's linear, so superposition is kind of built into it. 3, it's consistent with the conservation of momentum and energy. And 4, it's consistent with de Broglie's idea of the relationship between a particle's wavelength and its momentum. So if you want those 4 things to be true, the Schrödinger equation is by far the simplest way to do that.
And while the Schrödinger equation is not useful in every single situation, for example, we mentioned that if you have something moving near the speed of light, also known as relativistic particles, then you will not use the Schrödinger equation. You'll use the Klein-Gordon equation or QFT in general. But that doesn't make the Schrödinger equation any less useful. In fact, in quantum computing, in condensed matter physics, all these situations where, we're not necessarily colliding particles at great speeds, but we're just looking at atoms and how they behave, all of these situations can be understood using just the Schrödinger equation.
The Schrödinger equation has been put through an incredible gauntlet of experimental tests, and it just keeps passing them as long as everything's moving well below the speed of light, that is. Quantum mechanics, along with general relativity, is the most empirically successful theory in the history of science. So that thing that Schrödinger wrote down in 1925 has done pretty well. I think better than anybody expected at that time.
Why This Universe is produced and edited by me, Shalma Wexman, and my co-host is Dan Hooper, a physicist at the University of Wisconsin-Madison and the director of the Wisconsin Ice Cube Particle Astrophysics Center. If you want to support us, consider subscribing to our Patreon for as little as $3 a month. And in return for your support, you get ad-free episodes and the ability to ask us questions directly for Ask Us Anything segments. You can find that on patreon.com/whythisuniverse. Thanks for listening.